I'd like to introduce Mandy Waite, our cloud developer advocate and general cloud miracle worker, who's going to let you know what what developers would like in the cloud. Mandy.
Hey guys, can you all hear me? Ooh. Right. So this is one of the world's longest stages, so I have to walk down here every now and again and say hi to you lot as well. Hello. So I'll try and give you all an equal amount of love by walking backwards and forwards. So we're going to talk about what are game developers looking for in the cloud. So how many people here today are using the cloud for some part of their application, backends and such like? Okay, all right, okay. So we're going to cover everything pretty much, from the basics to what the Google Cloud Platform looks like. And we're going to start off by this. So basically, this is a very quick introduction. This is where you are. You've developed your game. You've built your game. You have perhaps versions of your game for mobile platforms, maybe for desktop as well. You've done all of the work. You've had a designer go over your work, make it look really, really attractive, make the graphics look fantastic, provide the best user interaction experience within the game itself. You've read about all of the lessons that people have learned when developing games over the years. You've built a beta version and you deployed it, maybe to the App Store, maybe to the Google Play Store, maybe to Chrome Web Store. You've had 0 crashes, 0 hangs, so you're done, right? That's it. You don't have to do any more. But what if one of the key features of your application was social interaction, the ability to interact socially between users of your application? What if it was a multiplayer game? What if you wanted it to be a multiplayer game? What if you wanted to gather analytics from your game about the way people actually interacted with your game? So one of the things you might want to do is what they did with Ingress. How many people have played Ingress? This was amazing because we think at Google that everybody plays Ingress. But whenever I ask this question about how many people have played Ingress, I only get about 2 hands come up. So how many people know what Ingress is? Right, okay, so you don't play it, but you know what it is kind of. Okay, so Ingress is effectively a multiplayer game. It's more of a social experience than a game, effectively. It uses Google Maps to show you portals that you can go around and capture. There's 2 sides, there's the Enlightened and the Resistance. You have to capture portals or create portals. It has great social interaction experience. You can talk to each other via the application. But one of the most important features of it is that people get together in groups. They get their phones out and they walk around and capture portals or create portals together as social groups. This is social experience, social interaction at the extreme. But obviously, how do you build something like that? How do you build an application that has those kind of services? You can't just build this on the phone. There has to be some back-end component. So how do you get started when you're building a back-end for a gaming application? So the first thing you could do, and this is what you would have done years ago, maybe for some of us now, it wouldn't even occur to us to do this. You could actually just build a server. Buy a server, stick it next to your desk, stick it in your garage, stick it in your office, and then you can run your back-end component of your application from there. But will it solve all of your problems? Who installs all of the software on this machine? Who upgrades the hardware? Who fixes the hardware when it breaks? What if the connection fails to the internet? What if there's too much load? I'm going to talk about load more in a couple of slides. So these are all of the problems you're going to get when you're building something like this on a server that you own. And again, some of us today probably wouldn't even consider this as an option. But not so long ago, this was pretty much the only option. But now today we have the cloud. This is kind of my idea. Somebody else provided this slide, but this kind of resonates with me really well. This is what it looked like to build applications back in the old days. We used to build machines, configure machines. I first started with Sun Microsystems, in Kodak, working on Sun Microsystems machines back in 1989. And we used to sit there with tapes, loading tapes into machines, and it would take a whole day to configure a system. We would build the hardware, we would build the operating system, we would build the software stack, set up the database, configure users, all of that stuff we would have to do ourselves. So you could build all of this yourself. What about anticipating your load? What are you going to build first? How many people are you going to get using your application initially? What happens if you get tech crunch? What happens if you get slash-dotted and suddenly your load on your application increases rapidly, increases ridiculously rapidly overnight? How do you handle these kind of spikes? Does this have a pointer on it? Guess not. How do you handle traffic kind of spikes? The kind of spikes we see here on the left, where traffic will suddenly increase very rapidly because of some event that happened. Maybe your game was published in an article on TechCrunch or on Slashdot or some other key forum for promoting gaming applications. What about periods of inactivity? What happens if your game is kind of seasonal, that people don't play it all of the time? What happens if you over-provision your load, or for your load, you have too many machines available at any given time? What happens when those machines aren't being used? You're still paying for them. How do you handle linear scale? How do you handle exponential scale? All of these problems are things you would have to tackle yourself. When we look at the cloud, we see something like this. We have these options: infrastructure as a service, platform as a service, and pretty much do it yourself. We'll also talk about software as a service and backend as a service as well. When you do it yourself, you pretty much have to build everything. And it goes back to the slide we looked at before with the guy with the boxes, building all the way up from the operating system up to the application level. With infrastructure as a service, you get all of the virtualization layer. You actually get a machine provided for you, a virtual machine. On top of this, you install an operating system, usually provided by the cloud vendor. And on top of that, you install all the middleware, all of the runtime, and your application software as well. That's infrastructure as a service. Platform as a service is a little bit different because it provides the OS, the middleware, and the runtime. It effectively provides you with a software stack on which you can run your application and store your data. So which would you choose? Do it yourself, infrastructure as a service, or platform as a service? And we're going to explore that question a little bit more shortly. There's also backend as a service. And backend as a service effectively provides you with services that your application can consume directly. So things like messaging, pub/sub, the social interaction experience, analytics, those kind of things. And also you can use gaming services, which is what you're going to hear about quite a lot today from people like Daniel. Daniel was probably already introduced all of these already. So these gaming services, you can just plug into them very quickly. You just write your code to them. You don't actually have to build anything yourself. So what do you choose? Infrastructure as a service is great. It's particularly suited for applications and games that are latency sensitive, that have a requirement for a very low latency. And this particularly comes in to play when you have games like Jam with Chrome. Anybody see Jam with Chrome, Chrome experiment? Okay, so this effectively allowed users to get together in an application and play instruments together, interactively across the world. So one person would be playing the drums in Australia while another guy was playing the guitar in the US. And that requires very low latency. That requires something like WebSockets. So in that case, infrastructure as a service is perfectly suited for that particular kind of solution. It's also extremely flexible. It gives you the most flexibility of all of the solutions possible because you can build anything you like on it. It's a virtual machine. You can also reuse all of that code and database knowledge that you've built up over the years. You don't have to worry about abstractions. Anybody who's working for you who knows how to program a database, how to actually build a software stack, you can reuse all of that knowledge. IaaS is particularly suited for complex games. I mean, you can pretty much run anything you like on it, but if you have a really complex game, it may be the other offerings, the other solutions are not particularly suitable for you. When it comes to platform as a service, the sweet spot for platform as a service, and we'll look at App Engine shortly, is the handling of scale, the ability to handle scale. Those kind of loads that we looked at before, where we have huge spikes in traffic, we have levels where we're not actually using any resources at all, we have exponential growth or linear growth. Platform as a service is also great for providing services that allow for player-to-player interaction. So again, this goes back to Ingress. Ingress runs on a platform as a service, and it offers all of these features to you that make it very easy to access other APIs and services that allow you to build social interaction. Spiking user numbers comes back to scale. And this is pretty good for casual type of games. Games like Ingress. Games like Ingress. Then you have these gaming services. Flappy Bird. I'm not sure if I'm allowed to use this icon, but it was already there when I got the slide. So, how many people played Flappy Bird? Okay, you admit it at least. So one of the key things about Flappy Bird is not the gameplay. We must admit the gameplay in Flappy Bird isn't the best in the world. But it does have this wonderful social interaction in that you can see your friends' high scores. That service is very, very simple to kind of set up. Once you have your high score, you can see your friends' high scores, and you can compare your score with theirs and then try and beat it. And that's when you start playing it over and over and over again, until a point where you throw your phone across the room because you keep hitting a pipe. It's very easy to get started with these kind of services, and it offers things like high scores and achievements. It offers you the ability to go back to your device and play the game, put the device down, pick up a tablet, pick up some other offering, and play that game, picking up from where you left off within the game environment as before. Sorry. This is very good for very simple games, although you can build quite complex games with it as well. So this comes back to Ingress. So Ingress was built on what's known as App Engine, Google App Engine. This is part of our cloud platform. And the social experience that Ingress offers is very, very important to it. Platform as a service was key here. The ability to handle the kind of scale that a game of Ingress's size, again, although nobody seems to be playing it, so it's quite hard to know whether it actually needs to scale up to huge levels. So Ingress is built on top of Platform as a Service. So there's a quick quiz for you. Which company offers traditional hosting, infrastructure as a service in the cloud, platform as a service in the cloud, and backend as a service, and mobile platform as a service? So that's us. We offer all of those services. And again, I think you're going to go through all of these today quite a number of times. You're going to see this kind of circle. You're going to see things like AdMob, the Android Play game services, Chrome Web Store, More Play services, AdMob, DoubleClick Exchange, Google Cloud Platform, and Analytics. These are all the things that we offer in order to build up a gaming experience. So let's talk about the Google Cloud Platform. So how many people here have actually heard of the Google Cloud Platform? Okay, how many people have actually used it? Okay, so the Google Cloud Platform is pretty much a new idea. We started off with App Engine back in 2008. Since then, we've made available Compute Engine, another component of our cloud platform, and we're building up other services on top of that to make a comprehensive, integrated, complete cloud platform. So let's go over what that actually looks like. Well, first, a bit of history. So software innovation happens quite rapidly at Google. Back in 2002, we had a requirement for a file system that was extremely fast, extremely scalable, and very low maintenance for our engineers, something that they could just throw data at and not have to worry about it too much. So we built this thing called Google File System. On top of that, we built MapReduce. We published a paper. All of these are white papers. So MapReduce runs on top of Google File System. It allows us to run analytics across data fairly quickly. Then we have Bigtable. Bigtable is a NoSQL offering, which we built on top of Google File System, and which is now available as the Google Cloud Data Store. Effectively, this is what App Engine, our platform as a service offering, was built around. Then in 2008, we published a white paper on an application called Dremel, which we use internally. And what this came about from was the need of our product managers to be able to ask questions of data very, very quickly, to get answers back interactively, effectively, to be able to answer questions interactively and get answers back in seconds instead of minutes or hours. Ultimately, we wrote this tool called Dremel, and we published it since then as BigQuery, Google BigQuery. How many people have heard of BigQuery? Okay, so BigQuery, we should have a conversation about what BigQuery is, because it's extremely important for analytics and gaining insight into what your data looks like. Beyond that, we came up with a Google File System 2, which is called Colossus, and on top of that, Google Cloud Storage was built on. Cloud storage we'll talk about shortly, but that is our bucket store. It's an object store for large amounts of unstructured data. We're talking about pretty much any amount of data you like, up to 5 terabytes an object. Then we have Spanner /F1. F1 is its internal name. It was published as a white paper called Spanner, and this is distributed SQL in the cloud. And then finally, Omega, which is a task orchestrator. So if anybody's ever heard of Borg internally, at Google, we use this term Borg, and it's leaked out several times, but we have this thing called Omega now, or Omega, I'm not quite sure how to say it. I could spend too much time in the US. Omega, which is a task orchestrator, a very, very advanced feature that we've introduced recently, which has a white paper back in it. Then the Google Cloud Platform itself consists of 3 main areas, and they are compute, storage, and app services. On the compute side, when we look at these in more detail, we have App Engine and Compute Engine. Then on the storage side, we have cloud storage, which I've just mentioned, which is built on top of Colossus. And that, again, provides a bucket storage service for storing unstructured data. Cloud SQL offers you MySQL instances in the cloud. These are completely fully managed instances. So you create your database on an instance, you create your tables within the database, but you don't have to worry about managing the actual instance itself. Then we have the Cloud Data Store, which is our massively scalable, automatically scalable, NoSQL offering. This, again, used to be tied completely to App Engine. App Engine was effectively built around the Cloud Data Store, but now it's available as an API. And this is perfect for structured data or semi-structured data, and it doesn't require a schema. It effectively uses buckets of properties. Then we have application services such as BigQuery, and I mentioned BigQuery before, but imagine the need for running analytics very quickly across your data, either running interactively or through an API. BigQuery is effectively an API, but it has a console that you can use to interactively query your data. It runs very, very fast. It has an SQL-like syntax and can run across terabytes of data in seconds, billions of rows of data. Then we have Cloud Endpoints, which we'll expand on more, which effectively allows you to build APIs that are your interface into the cloud. So some of these cloud platform features that we feel are important to kind of call out here are the ability to scale. You want your app to scale. You want it to scale to Google scale. The ability to scale very quickly on demand. And scaling here, we're talking about, again, not just the ability to scale upwards to manage spikes in traffic, but also to remove resources when they're not needed, so that you have what you need when you need it, but you only pay for what you use. Also, because of the ability to auto-scale, you don't actually have to plan ahead for resources. When we use App Engine, we'll look at App Engine again shortly, App Engine will scale up, spinning up instances as required to meet the demand from the traffic to your application. Also, flexible charging. Again, we go back to what we said before, pay for only what you use. And this is quite important to anybody developing applications in the cloud. If you have resources sitting around consuming cost, that's down to you. But if you're having to pay for things that you're not using, say like you use a virtual machine for 10 minutes, 20 minutes, and you pay for an hour instead of just those 20 minutes that you're using the virtual machine, then that's not very efficient for you. Also, no large-scale investments. You don't actually have to buy machines. You don't have to buy a big cluster of machines or boxes. You don't have to build a database. And we have these startup programs that are available. Startup packs, a very simple starter program. Did you all get the little card? Yeah? So I think Rupert's going to talk about more about that later, but effectively that gives you some credits that you can use for the Google Cloud Platform itself. Then we have these RESTful APIs and the ability to integrate with other Google services at effectively what very low latency interaction with Google services such as YouTube, Maps, Google Plus APIs, and other services such as the Cloud Data Store, Cloud Storage, all of the other services we looked at before. Also, these APIs are supported by many third-party tools, and we provide tools as well for building APIs. And these are very consistent and standardized across all of our product range. And when it comes to support, we have free and paid support options. And our support team has real engineers. So effectively what we have are site reliability engineers, and I'll talk about more about those in a second. And we have a free 9s SLA for all of our products. So let's talk about App Engine. App Engine, again, the ability to auto-scale, we've covered this already, so I won't go into any more detail. But it's very easy to get started with Google App Engine. It's free to start. There's a free tier. You don't have to put your credit card information or any billing information in. Effectively, you get some quotas you can use for a day. They get reset on a daily basis. And that's really good to get started with. And also, we provide you with a local development environment. So you can do all of your development interactively on your own workstation or on your laptop before deploying your applications to App Engine. It also offers these service abstractions to the Cloud Data Store, to Memcache, that are very easy to get started with. You don't actually have to build Memcache servers. Memcache is available to you directly. We have abstractions that allow you to access the data store very, very easily within your code. It's also extremely trivial to manage. So App Engine is fully managed. It provides software stacks in the cloud. Currently, we support Python, Java, PHP, and Go. No patches. You don't have to worry about patching or upgrading these software runtimes. And they are operated 24/7 by what we call site reliability engineers. These are the guys that wear the pagers. These are the guys that get woken up at 2 a.m. in the morning to fix issues with App Engine. Then Cloud Endpoints, and I've mentioned Cloud Endpoints briefly already. Cloud Endpoints allows you to expose your application code as an API. And what you do is you write your application code, you deploy it to App Engine, you can then add some annotations to your code, or you can build this all from scratch, add some annotations to your code, deploy it to App Engine again, and you will effectively have APIs that are running on the Google infrastructure, the Google API infrastructure that we use for exposing our own APIs. These APIs are completely discoverable, they're RESTful APIs, and they're very, very easy to use. Once you have the API exposed, you can use tooling that's available from Android Studio, Eclipse from the command line to build client libraries, which can then be consumed by your applications, either Android, iOS, or JavaScript. All of this comes with built-in authentication support, so it's very, very easy to use in terms of authenticating users. Cloud Endpoints looks something like this. It's very, very simple to use. You'll start off, this could be brand new code, or it could be something you've exposed already to web-based users, and now you want to expose it as an API that can be consumed directly from another application service. So in this case, we have a method called submit answers, and we've annotated it with a method called @API method. Here we're actually saying we want to use HTTP method put. Some of these things can be inferred by the runtime. If we call this method insert answer or something like that, then we could infer that that would be a put. So get answers would also be inferred that that would be a get method. But we can specifically say this in the annotation. It has very, very, very standard defaults that it works with. You can also specify the path. Again, that can also be inferred by the class name, by the method name. In this case, the path is game/ID. ID is a parameter, which we're going to call out later, /answers. So that would be the path for our RESTful call. So submit answers is our method. It takes a couple of parameters, well, 3 in this case, game ID, answers, and a user object called player. We've annotated the game ID with named ID to give it a name, effectively, and that's used in the, I wish this had a pointer on it, and that's used in the path in the original API method declaration. The user object itself is injected into the call by the runtime. It's not something you need to provide. So when this method is invoked by a user that's already logged into Google, the logged in user will be injected into that call, into the API call. Then we can actually check to see if the user is logged in. If user equals null, we can throw an unauthorized exception saying this user is not authorized to use this method. Effectively, they would require to be logged in at that point. Then we can call gameService.submitAnswers, which is some other abstraction we've built somewhere else. When it comes to actually calling this method from within an Android application, we would build a client library from this code. It's very easy to do. There's tooling, as I say. In Android Studio, you can just say build Cloud Endpoints client library. Same thing with Eclipse. And once you have that, you can build your application around that client library. And effectively, what you would do is you'd call service.gameEndpoint. That would give you the endpoint itself that you can consume within the application, and then you would call submit answers on that. So service.gameEndpoint effectively represents the client library, the stubbed out client library, which will make the calls to the API. And in terms of tooling, that looks something like this. This is a little bit out of date now, but we have tools on the command line. We have this tool called gcloud, the Cloud SDK, that can call all of these methods for you. And here on the top line, we see the client library being generated. And you can also do the same thing with an Eclipse and with an Android Studio. Compute Engine offers virtual machines and block storage in the cloud. It also offers load balancing and networking, all of the compute resources you need to build clusters of machines. And there's going to be some announcements today that are actually going to put a new spin on this as well. It's also cost-effective, sub-hour billing. You only pay you pay always for 10 minutes of your usage of a virtual machine. But beyond 10 minutes, you only pay by the minute. So if you use a virtual machine for 15 minutes, you'll pay for 15 minutes, not for an hour. That's extremely cost-efficient. We also do not charge IOPS charges for block storage. Every machine needs block storage. Every virtual machine needs block storage. And we do not charge for IOPS to your block storage devices. So you effectively just pay by the terabyte. And we don't need to provide virtual machines for load balancing. Our load balancing is actually effectively built into our network infrastructure. It's also consistently fast. We have very fast instance provisioning. We can bring up 1,000 virtual machines in under 2 minutes. I was going to do a demo of this, but I decided not to because we have this big event going on today. And if I did something that inadvertently caused our cloud platform some issues, I would probably get it in the neck. But so I'm not going to do the demo. But normally we do this demo that shows 1,000 virtual machines being spun up in about 1 minute 30 seconds, 1 minute 45 seconds. Consistent disk performance is extremely important as well, because if you run an application within the cloud, you want to avoid this noisy neighbor problem. You want to avoid the operations that somebody else is performing affecting yours. So we have very consistent disk performance. Also, our cloud-native load balancing requires no warm-ups. Most load balancing services require a warm-up period. Ours is instantly on. As soon as you start using it, it will be available to you. And Google BigQuery, we've talked about that quite a bit already. But effectively, import data into BigQuery. Once you had the data imported into BigQuery, you can run queries interactively or via an API across that data. And that allows you to ask important questions of the data. If it's gaming data you're looking at, you can be interested in things like daily active users. What is the user doing? How is the user interacting with the application? What can I do? What actions can I take in order to improve the experience for the user, for the player? And what you would do is you would constantly run these analytics on a daily basis, getting graphs and charts, automatic based analysis of the user's interaction, sending them offers and such like at certain points in their user experience to try to get them to use the game more. It's extremely affordable, and you'll see more about this later. First 100 gigabytes per month for free. We have a very simple pricing model, and we have a validator that tells you the size of a query when you run it. So you can actually predict how much a query will cost. It's extremely easy to use. It's built for scale and performance. Very simple SQL queries, and it has open interfaces for REST and JDBC. In terms of what we're going to announce today is something called Managed VMs. This has been available in Trusted Tester for some time now. It used to be called VM runtimes. And what we're trying to do here is to blur the lines between infrastructure as a service and platform as a service. So it's no longer a binary choice for you. So you don't actually have to make a choice between infrastructure or platform as a service. You can choose one and then move towards the other. And this is facilitated by this thing called Managed Virtual Machines, which effectively allows you to use App Engine as your front end, but to use Compute Engine virtual machines as backends, backend modules effectively of your application that can run anything you like. So we talked about platform as a service, App Engine being able to run Go, Java, PHP, and Python. But what happens if you want to run Node.js? So you can run that on infrastructure as a service, on Compute Engine, but still have App Engine manage those virtual machines for you. So that's effectively blurring the lines between platform as a service and infrastructure as a service. So again, going into more details about how you would choose, infrastructure as a service has its sweet spots, compute workloads, Hadoop map reduces, those kind of things. Running simulations, running Monte Carlo simulations, running complex workloads. Platform as a service is great for game backends, mobile backends, web type workloads, things where load is unpredictable, where you require auto-scaling. Both of them work brilliantly for background processing. You can do background processing with platform as a service or with infrastructure as a service. But when it comes to things like running Node.js, you need root access to your virtual machines, you have C++ libraries you want to run WebSockets, then you're going to need to move to infrastructure as a service. So Managed Virtual Machines allows you to do both and fills in that gap between infrastructure as a service and platform as a service. So a complex app architecture would look something like this. We have all of these services at the top here, which are App Engine services, the data store, Memcache. We have things like task queues, full search API, mail service, cloud storage API. Then we have modules. We have 2 App Engine modules. And App Engine is completely modular now. So we have 2 App Engine modules servicing web traffic. These are autoscale modules. They have the ability to autoscale to meet user demand. But over here, we also have another module, which is a VM-based backend module, managed VM module that we built using the infrastructure as a service virtual machines. That gives us full access to the App Engine APIs, but it gives us full control over the virtual machines. And just one thing I wanted to mention, I kind of added this slide at the last minute because I realized I kind of left it out, is the ability to do VM orchestration. So App Engine can manage infrastructure as a service virtual machines directly through an API. So Compute Engine itself has its own API. We can use App Engine to spin up new instances on demand, effectively to manage autoscale for us. So if we have a game that requires back-end gaming servers, we need to provision more servers as the load increases, then we can use VM orchestration on App Engine to actually fire up new servers, new game servers on demand. In this case, the example shows a heartbeat process with the VM orchestration service actually checking the heartbeat process, looking at how busy that particular server is, and making decisions on when to spin up new servers or when to bring servers down. This is a reasonably complicated architecture, and it's one of the sample applications we have published on cloud.google.com. And again, in terms of gaming, we have all of these amazing studios that are using our cloud platform, including Rovio, GameSys, Chilingo, and also Songpop. So Songpop basically built their game with just 3 or 4 developers on a project. They didn't need to worry about building any infrastructure. They're now up to 1 million daily players already. Well, they were up to 1 million daily players already 2 weeks after launch. And now I think they're at like 2.4 million. They serve effectively 18 terabytes a day to 80 million users. Okay. And there was a talk, I/O 2013 talk, Google I/O, called Intense Gaming, that kind of went into this in more detail. And in order to get started with the Google Cloud Platform, it's completely free for using App Engine. We can give you credits for startups. If you're a startup, we can give you credit packs. Documentation and tutorials are available on developers.google.com. In this case, it's just for App Engine itself. And if you're interested in the starter pack, you have the little cards. You can claim those credits and use that code there, thesummit-con. And that's it. So I think we're out of time for questions. So if you want to catch me at lunchtime, if you have any questions. Yeah, you sure? Okay, yeah, so any questions? Hey, so
Can we grab the microphones for questions, because they're being recorded as well? Thank you. Or we'll just repeat.
Do you have your servers running in China as well?
running in China?
Yeah.
I don't think we have a data center in China.
Okay.
We have a data center in Taiwan.
Yeah. Well, might be an opportunity, but it's.
Okay, so is that something you're interested in?
Yes.
So you had game users in China?
Yes.
Okay, right. So what are you using currently?
We're building up our own infrastructure.
You're building up your own infrastructure?
Yeah.
Okay, all right.
It's like Amazon has told that they are doing something in China as well, but they're working with local services, so it's not the same as actually what they do in the West.
Right.
So it's actually trying to find out together with Chinese people over there and trying to sort of like mirror what we have over here. But
Okay.
it's a huge cost to build up your own data center, and yeah, it's a lot of work we shouldn't be doing because we need to create games. So.
Yeah, so I'll maybe watch the announcements today at the live event to see what they're going to announce. But yeah, we don't have any data centers in China at the moment. But you're right, it's a huge place, and it would be great to have data centers there. But maybe there are some concerns about security and such like as well.
Probably, but
okay.
Cool, thanks.
Cheers, thanks. Any more questions? Okay, all right. So,
Thank you very much.
There you go. One more.
I was interested to hear a bit more about the auto-scaling. The last bit you mentioned, which was about scaling up and conversely scaling down on demand. Can you run through that again? Because that's most interesting to us.
Okay. So when it comes to App Engine has this thing called autoscale, the ability to autoscale, based on a very complicated algorithm. Effectively, it will monitor traffic. When a new request comes in, it will say, do I have an instance available that can service that request? Do I have a parameter set in called pending queue latency that will tell me how long that request should sit in the queue? If it's going to sit in the queue for longer than that time, based on my algorithm, I can spin up a new instance to service that request. But then maybe there's an issue, maybe it takes too long to spin up the instance, so you can have these things called idle instances as well that can service requests that can't be serviced by an instance currently. So effectively what we have is the algorithm that will spin up instances on demand, will queue requests for a given amount of time based on your parameters, and we have idle instances that can be used to service requests that can't be serviced by anything else very quickly. So that's effectively how the autoscale works. The instances come up very quickly and they scale down very quickly as well. There's no timeout period. We look constantly on the load on the machines, on their pending queues on each instance, and if we see that there's no jobs queued for them, we will tear them down once the current job's finished. And so it's very efficient. We have the ability to scale up very quickly and to scale down very quickly as well. Does that make sense? Yeah, okay, cool. Okay, so good. Thank you, Rich. Thanks for the time.
Thanks very much, Mandy.
Cheers.